What's up guys, and welcome to this video on question 6 of the 2016 final exam. We're going to go over this question which has to do with fields. Again, it's one of those questions, 19 marks, but it's not really about fields. It's actually mostly about drawing graphs and whatnot, which I don't enjoy because I don't have access to graph paper on this. So I'm mostly going to go over the process of how to answer these, and I'm not really going to focus too much on the actual numbers, but how to actually do the question, the methodology rather. Okay, hopefully you guys find that useful, and it's really simple actually, not too difficult. Okay, getting into the question. David is curious as to how the electric field at a fixed distance away from a charged sphere depends on the magnitude of the charge on the sphere. Okay, so this already speaks of a relationship which we know of, which is that the electric field is equal to K, Coulomb's constant, Q over R squared. Okay, but we'll see if that becomes relevant later or not. But it's important just to know that we do know a relationship. Okay, then we can move on, and says David charges the sphere positively and measures the electric field at a distance from the center of the sphere. During his investigation, he repeats the experiment, each time changing the magnitude of the charge of the sphere. Okay, so this we can identify as the independent variable. Okay, so the electric field strength must be the dependent variable. Okay, it's good to just ask yourself these questions and note down what you can, because there's a chance it comes up as a question. Okay, so question 6.1 comes out as a definition, which says define electric field. Okay, so an electric field is the force per unit positive charge. Okay, and we get 2 marks for that definition. Good stuff. And then it says draw the electric field lines around a positively charged sphere. Okay, so 6.2. So if we have a positively charged sphere, okay, so we know that from the previous definition, the electric field is defined per unit positive charge. Okay, so if we place the positive charge, another one here, what's going to happen? Okay, so it's going to get repelled. So basically our arrows are going outwards for a positive sphere in all directions, but you can probably draw, what is that, 8 arrows and call it a day. Okay, and we should get 2 marks for that. If it was a negative sphere, we would have the opposite. Hey, we'd have field lines coming inwards from all directions. Okay, cool stuff. Then it says state a hypothesis for this investigation. Okay, okay, so we've already investigated, or we've already identified the independent and dependent variable, right? So we know that the independent variable is this variable, which is the magnitude of the sphere, and we know that the dependent variable is the electric field. So a hypothesis, we need to say what we think is going to happen. Okay, and we can already see from from this table what's actually happened. As our independent variable, or the magnitude of the charge increases, so as Q increases, the electric field strength also increases. Okay, because we can see we're going from 2 to 5 and we're going from 6 to 19. So, and that continues to increase. So we can say something like, as a hypothesis, we can say that electric field so we can say that electric field strength, so this is our hypothesis, which is like a guess, an educated guess on what you think is going to happen. So I think that the electric field strength is directly proportional to the let's say Q, which is charge. Okay, so basically I'm saying that I believe that as Q increases, E, the electric field strength, is going to increase. Okay, and we see that happening, but we're not sure if it's directly proportional. But that's what I'm just going to assume. Okay, and then comes plotting of the graph. Okay, so let's see. I'm going to draw a rough sketch as per usual, nothing too hectic, but remember, always put in a heading. So for this, we can say graph showing electric field versus charge. Okay, then I'm going to have, so electric field must be on the y as that's been given to us, so I'm going to have E, and I'm going to put my units kilonewtons per coulomb, and on the other axis I'm going to have Q, which is in nanocoulombs. Okay, important for when we, or if we have to do some calculations, that this is times 10 to the 3 and this is times 10 to the minus 9. Okay, important to note that. Okay, then if you plot your points, basically you will get a straight line, something that looks something like that. Okay, and you can have your values going up in tens, let's say, because we need to get to 60. I mean, we need to get to 50 because our electric field strength gets to 50, and I think it spreads out nicely over 60. And on the other axes, let's say we go up in twos, 2, 4, 6, 8, 10, 12, and we need to get to 14. Okay, so something like that. Okay, and your points, remember, don't have to lie. So there could be points here, here, here. One point might actually lie on the line, but they don't necessarily. You're just drawing a line of best fit. Okay, and we get 6.6 marks for that, which is quite nice. Okay, then it says calculate the gradient of the graph. Indicate the value that you used. Okay, so for the gradient, all we're going to do is pick 2 points, and we're going to say gradient is equal to change in y over change in x. So something important to do is make sure that you pick values. They don't have to be the points given here. In fact, it's better if they're not these. Try to not pick these points, but to rather pick points that your graph actually cuts. So let's say your graph cuts nicely here with 20 and 4. Even though that isn't a point that I've been given, I'm going to pick that as my first point, let's say, and I'm going to pick a value here because it's nicely lines up with 40 and nicely lines up with 8. Okay, so they don't have to be these points that we plotted. In fact, it's better if it's not. It just needs to be on the straight line. Okay, so once we calculate the gradient, we'll get some value. Okay, and we will have units of some weird units. We will have units of, let's see, it's going to be change in y, so it's going to be coulombs, kilonewtons per coulomb divided by, so nano coulombs to the minus 1. Okay, nano coulombs to the minus 1. Okay, so I hope that makes sense, the units. So basically I'm just saying, or I can even say, might be better doing it like this. So I am saying it is kilonewtons per coulomb times 1 over nanocoulomb. So it's going to be kilonewtons per nanocoulomb squared. Okay, so either one of those works. The other format, like I said, was kilonewtons per coulomb times nanocoulomb to the minus 1. So this minus 1 applies to both of these. Okay, cool stuff. And we get 4 marks for that, for calculating the gradient and giving the correct units. So that's quite generous, I think. Okay, then it says use your answer from question 6.5. Your knowledge of electric fields and the equation y equals mx plus c describes, and that the equation y equals mx plus c describes a straight line to determine the distance from the charge at which David made all the measurements of the electric field. Express your answers to 3 decimal places. Okay, so let's read that nicely once again. Okay, so use your answer. So use the previous answer. So the value that we got out of there. your knowledge of electric field strengths. Okay, so my knowledge of electric field strengths is going to be this equation. Okay, this is my knowledge. This is what that refers to. And the equation y equals mx plus c. Okay, so basically it's trying to say, use the fact that, so for 6.6, I'm going to say that E equals kq over r squared and y equals mx plus c, right? But my c, because it goes through the origin here, goes to 0. So what's actually happened is we can say that my gradient, okay, so my gradient was equal to k over r squared. Okay, so does that make sense? Because that is my m. Okay, so my m, this m value here is going to be k r squared. Okay, and then I'm multiplying it by my x value, which is q. Okay, I hope that makes sense. So if we compare, so basically what we're trying to do, let's erase this and go one step back. So now we're left with, we know that c is equal to 0, so we're left with that, right? So now what I'm trying to do is figure out, I'm comparing these two equations, and I'm trying to figure out what is my m and what is my x. Okay, so it's, okay, I already know y is equal to E. So electric field strength equals E, right? And then I'm left with m or x. Okay, what is my x? My x is q. Okay, so q. So therefore, my m must be whatever's left over, which is k over r squared. So therefore, we can say that the gradient is equal to k over r squared. So we can say we know what the gradient is. The gradient is the value that we calculated right here, is equal to, we know what k is, because that's just Coulomb's constant, which is 9 times 10 to the 9. So the only unknown is r. So we can solve for r, which will have something in units of meters, some value. I'm assuming it's going to be a 3 decimal. It's going to be important to 3 decimal places. That's what they've told us. Okay, so I hope you guys were able to follow that. I know it's not great because I can't actually do the entire question, but I think most of this question was theory-based and could be explained quite easily. Yeah, and with that, this paper is done. So yeah, cool. Thanks for watching, guys. I hope you found this useful.